Hello, Jimmy. How are you? Okay, so we have about a minute before we start. Oh, good. Thank you. I'm doing well, thank you. Hi, Joseph. If we can log into Canvas, check out your notes and your assignment. We'll do that together. We're going to cover parallel processing today, Chapter 7. So we'll start in about a minute, okay? Before we start, if you have any questions, let me know. Okay, I'll go ahead and continue. Hopefully more people will join us. So this week we are going to cover Chapter 7. This is going to be parallel processing. We're going to continue to look at asynchronous programming. And this is a different approach from what you've seen from last week. We are going to use multiprocessing module, which is included with your Python package. So for most part, we don't have to install additional package when we run the program. The majority of your programs will work in your IDE as long as you have your IDE properly linked to your Python package. So you don't have to install additional things, but we'll talk about the lab, how the lab options can be in Linux or your IDE. So we have a little bit to do today as far as parallel processing. This chapter is a little bit lengthy. So we'll go over the concept and then answer the questions and do some programs. Okay, so at the start of the notes, it defines what parallel processing is. And this is a way that we can use our multi-core processor to execute tasks. It doesn't necessarily be faster than what we've seen in the last week on how we would program asynchronously using task. But in this one, it shows you a different approach on how to use distributive memory allocation. So in parallel processing, we want to have the task execute simultaneously. So that way we can allow the program to be multitask. And for Python, multiprocessing module is going to be the package that we're going to use, or the module that we're going to use for parallel processing. Now, multiprocessing module been around since Python 2, but is adapted for Python 3. So you can leverage your multi-core processor. So in my case, I'm running 8-core. That allows me to utilize all my cores for the application when it runs. Now, the way that we want to think about parallel programming when we design is we need to really handle the data communication on how the data is stored. So we can put the process in separate memory locations, or we can put it into one shared location. So the first approach is the shared memory, where the subunits is going to have to access the same memory space where the data is stored. So you don't have to handle the communication if it is using shared memory. And if you have multiprocess, what will happen is it would try to access the same location at the same time. So in a synchronized approach, we would see that there would not be such conflict, but in asynchronous programming, as it's utilizing the same space, you might have some hang up in the multiprocessor utilizing that same space. So we can think about how we can divide that up into threads, and threads can be treated as independently subtasks, as you have seen in the past, and we will continue to work with some additional module for threads. So that way, even if we're using the same shared resource like memory, it's not going to create any conflict when we are accessing that same location. So here it talks about how you can have multiple execution in the same space. And so when you visualize this, what we can see is when we create multiple threads, individual thread can access that same space if using the same shared location. Now, if you're using distributed locations like this, you can implement multi-processes using multiprocessing module, where individual process would access individual memory location for its task. So that will be the two approach that we're going to see. And so on the first page, it shows you the diagram on how that would be different. So when we create threads, that's considered spawning the thread. And we can have a thread pool, which is a group of threads, and each thread can be a subtask. So now here it says that when you spawn and handle the thread in Python, it cannot be used to increase the performance. Because when you think about how we talked about GIL last time, which is your global interpreter lock, this really requires us to only have one instruction to run at one time, at each time. So as each of your thread executes the Python statement, it requires GIL. So once it's done, then it's going to release the lock, and so that way when the execution is complete. And we're going to come back to this concept also toward the end of the class when we talk about handling some of the issues with the hang-up in Python. So when you have threads that are preventing others to execute, those threads will hold on to the lock, and so therefore you might have a delay in the program completion. So that's the disadvantage of using the threads. So when you're using the shared memory and you're creating the thread pool or spawn the thread to handle the task, you might come across that issue. And even though we see that in concurrent programming, threads can be used, and when the locks is released, we do see that there is some time consumption in I/O operations, or even if we're using the C extensions. So that would lead us into the distributive memory. And so in distributive memory, as we saw on the first page, each process is going to have its own space. So we will require to have more storage, and that storage space is going to be cut up into individual smaller space for each of the process. And each process has its own interpreter. So it is going to be treated as an individual component. So therefore you would see that it's using distributed memory. Now this tends to be slower than when you're using a new thread when it initializes, and it consumes a lot more memory. And the intercommunication will be slow for the process. However, this can be flexible and scalable. And especially when you are using distributed on multiple machines. So in the case where you're thinking about servers in the distributed environment, such as your cloud servers and so on, that will be more feasible, even though it requires more memory and it might be slower than your threads using the shared space. And so when we handle the communication, it will be explicit for the process. And so when you're looking at the resource, that means that your program, the overhead for the communication is going to be more costly compared to what you've seen if we implement threads. So in this sense, you really have to consider what kind of technique you want to use to really address your objective. So you have options in how you can implement concurrent programming, and to think about what kind of resources you have on hand. So if you're limited with RAM or memory or storage, what you should consider is looking at spawning thread. But if you're able to implement a solution for something that would be distributed, and you want it a little bit more responsive compared to synchronous programming, then you can think about distributed memory with multiprocessing, or what we call parallel programming. So in the first question, let me come back to the top here. I was just checking my work. It asks you to define what is parallel processing, and in Python, what module can be implemented for parallel processing. We can say that parallel processing is a mode of operation where the task is executed simultaneously using multiprocessor. And in the current modern processor, you would see that all processor would have multi-core, so we can capitalize on the multi-core architecture to be able to implement parallel processing. And that really means that compared to a synchronous program or a single processor running the program from top to bottom, right? We would see that it would reduce the overall processing time. So here I put that it's meant to reduce your overall processing time. Now for Python, we would use the multiprocessing module, and mainly because we want to use it to have our parallel processes run independently using sub-processes instead of threads. And that can be implemented with shared or distributed memory. Usually with this, we would use distributed memory. Then for question 2, it asks you, how is data communication handled in parallel processing? We can say that it would use shared or distributed memory, as we define that on the first couple of pages in our notes. Any question? Okay, so therefore we can break down, and you don't have to put everything verbatim, right? You can use what's in the notes, or you can summarize. So for number 3, it asks you to differentiate between shared memory and distributed memory. How are they used in Python? In shared memory, the subunits have access to the same space. So you don't have to explicitly handle the communication as a developer. Now, the problem with that is when our multiprocessors try to access and change the space of your memory location at the same time, that can cause some conflict. So we would use synchronization technique to avoid the conflict. And that would be the solution. And then I note that a common way to achieve parallelism is to use thread for shared memory. And we mentioned that distributed memory, each process uses its own space, has its own interpreter, and it is normally slower than starting a new thread. That means that it would be more costly because it consumes more memory and the inter-process communication is slower. But it is ideal for distributed on multiple machines as the processes are flexible and scalable. So in distributed memory, we also mentioned that we need to handle the communication explicitly between the processes. So our overhead for communication would be more costly compared to your shared memory. Now, when you look at this in a network span, so let's say that I use this for all my servers in my network, then I can think about how the communications where the data is stored, right, on the distributed servers or systems has to be communicated across the networks through your network interface, which could be just adapter, right, or adapters. Some servers would have multiple adapters. So it has to really pull the data at separate location and to be able to use the combined data to execute. So therefore, we see that it's a little slower. Any question on this? Okay. So for parallel processing, we're going to come back to the notes now, and you can find the answers for that on page 1 and page 2. We should also talk about GPUs, so your graphic processing unit, and most of you know this because as you upgrade your video adapter for gaming or animations or video editing, etc., right? So for graphic processing unit, your GPU, the processors are really designed for graphic based. So for like 3D or animations, and it would use array and matrix operations on floating point numbers. So GPUs are really designed for parallel architecture compared to some of the CPU. GPUs have more processing units. So that way it's able to handle the data at a higher frame per second. However, most of your GPU is clocked slower than your CPU, which is why what we would see is it is an added component or added an added component to your system in addition to your CPU. So to compile programs for GPU, and you do see this, a lot of people have started using GPU for like machine learning and so on, right? So when you write the program and you want to compile it for GPU, you can use platform like CUDA or Opencl. And CUDA stands for Computer Unified Device Architecture. It is proprietary to NVIDIA technology. So this is made for adapters that utilize NVIDIA. And with that, we are able to integrate API. So it is a way that we can use a program to interface with another program. So through the API, we're able to access from other languages, and it is not tied to a specific language. And so under CUDA, it uses the NVCC tool to compile the program, and ultimately it is C language. You can implement multiple libraries that would be for mathematical routines, and I also include the link for your CUDA toolkit. The second option that's mentioned above is your Opencl, and this is open technology. It is not proprietary to a certain product or company. So compared to CUDA, which is proprietary to NVIDIA, Opencl is open technology. So if you're using other architecture or other type of technology, you would consider using Opencl. And with this, we're able to write parallel programs that is compiled based on for the CPU or the GPUs for different vendors. And there is also a link to Opencl. So as you know, most video adapter comes equipped with additional storage, and that was the main benefit. It has its own memory location, so that way you can capitalize on that. However, we need to really consider how the memory transfer from its location to the main memory. So that means that we probably have to implement algorithm to be able to either set up that communication explicitly or transfer the data to take the advantage of the GPU architecture. So it doesn't mean that if you store it onto the memory of your GPU, that way that's done. We actually have to consider how we're going to be able to have access to that data by transferring or set up the communication for the data. And because for the performance, why GPU is really used is because it has high throughput. So the number of the operations that's performed per unit each time is going to be higher. While CPU is faster in the producing the result, it does have some latency. Okay. All right. So latency just means that it's slightly delayed. However, your CPU clock rate is higher. Okay. So that section really addressed a little bit in comparison. If you're using GPU to compile your program, what should you use? And then in comparison with the CPU, where we would have multi-core CPUs against GPU and how that would be different. So to answer number 4, compare the CPU, how is GPU produce data for graphics applications? So GPUs have thousands more processing units, which produce data at approximately 60 frames per second, and it is slower than CPU clock speed in general, and that's a generalized statement, right? And we do see a huge growth in development for GPU as it is highly demanded for different areas, from Bitcoin mining to implementing for machine learning, or even for gaming purposes. So, you know, in the upcoming years, we might see that this technology will pick up and even exceed or be better than what you see with the normal CPU. And for 5, which platforms can be used to compile programs in GPU? We talk about CUDA, so Computer Unified Device Architecture, or Opencl. Let me push this up a little. So those are the 2 type of platforms that we can use to compile programs for GPUs. One is proprietary and the other one is open technology. So it really depends on the type of GPU that you have, right? Or you're using. So if you're using NVIDIA-based technology, you would use CUDA. If you're using other technology that is not NVIDIA, you would consider using Opencl. And there are other GPUs are available. So I don't know if you probably heard it on the news, right? There had been some changes with NVIDIA. And so with their video adapter production and so on. So that really changed how NVIDIA market's going to be. So we will see how that's going to end up, as there had been contract that's discontinued with NVIDIA. Any question? Okay. So again, coming back to your notes. Okay. You will find the answer for that on page 2. Now, when we start using the multiprocessing module, you can take a look at the documentation. It does support Python 3x. So the process would be that for parallel programming, we would spawn the processes while avoiding GIL. So it is easy to use as far as the interface, and we can synchronize the task. So when we use the multiprocessing module, there are 2 main objects that's going to be implementing. We have a pool class and a process class. Those are the primary classes that you would see from this module, multiprocessing. And through the pool class, you would see that we're able to access the methods such as map, star map, and apply. So the example below, I pulled this from their documentation. This is a way that we can implement functions for parallel processing using multiprocessing module. So you would have an import statement, and from that import statement, we are going to pull in the pool class. Then we would define a function called f. We're going to pass x in its parameter. Then we would return x times x. And then we would call. So in the main, unlike a regular synchronous program, you simply call f, right, in main. Because this is a pool of processes, you are going to use the pool object here. So this is where the pool class comes in. And we want to say that we are going to access the process as a loop. And we're going to use the map method to call f, which is our function from above. So then we're going to pass the value 1, 2, and 3, and that's going to plug into for x. So 1 times 1 is going to give you 1, 2 times 2 is going to give you 4, and 3 times 3 is going to give you 9. So slightly different than your regular synchronous program. What you can see is you would create a pool of processes, And through that, each of the process is going to call the function, and it's going to plug in the value so you can produce the output. Now we can do it this way, but we would properly do it when we want to spawn the process. So in multiprocessing, you need to spawn the process. That means that you are going to create the process object. And then you need to call it using start method. So similar to what you've seen in the last example, in this one, we have a function and we're going to print out hello, and then we're going to plug in name. In the main, we create an object called P, and this object belongs to the process class. Now, the important part right here is your parameter. Your target, you always have to state what your target would be. So your target is going to be the function that you define, what you're trying to execute. So here we're going to bring down F because that's the function. And for that function, we're just simply going to say hello and name. And then for the arguments, what we want to plug in for name is going to be Bob. So it's going to say hello, Bob. But to spawn this process, we're going to say the object, right? And then we're going to use the start method. So you would say p.start. Now, after we spawn the process, we need to join it. So basically it's going to call. So you're always going to have an object that instantiated for the process class. Your target is going to be what you're trying to execute, which is your function. And then additional argument for that function. Then you're going to spawn and you're going to call. Okay, you're going to execute it. So by joining, what we can see is we are going to be able to execute that after we spawn the process. Let's look at another example and then we'll do the next question. So this one, it's going to show your process ID, and you saw some of this last week. So here we are using multiprocessing module, and we simply use process class. Then we're also going to use the OS module, and usually OS module is used for like processing the process ID or access the process ID. So in the function, we have info. We would print out the title. We would print out the module name. Then you know that the process would have the parent and the child process. So that means that the primary process and its sub-process. So we would print out the parent process and the sub-process or the child process. Then the second function, we have the function F. It's going to call info function, and it's going to pass function F. Then we're going to print hello name. In the main, we're going to call info and pass mainline. Here again, you have an object called P instantiated for process class, and the target is going to be the F function, just like the last one. And then we're going to pass the argument. We are going to spawn and then do the join. So for start and join, they go together. The start is going to start the process activity. So that's when you spawn. This needs to be called at most once per process object. So you need to call it for each individual process. What it does is it actually uses the run method to invoke separate process. similar to what you've seen in the last week where we used run from async IO, right? So when you want to start the process activity, you would say start. For join, this method blocks until the process whose join method is called terminates. So it's gonna go until the call is terminated. And in the argument, you can also state the timeout, but if we by default we leave it blank, right? That will be none. So it's gonna check to see if the process is terminated, because remember that we talked about how it needs to be blocked. So the process can join anytime. And the process cannot join itself because it would be causing a deadlock. So when it causes a deadlock, you would have an error. So when you use the join method, what it does is it blocks the execution of the main process until the process whose join is terminated. Okay. Remember that it cannot, if it doesn't block it, the main process is going to try to execute and you're going to have a deadlock. So without the join method, the main without the join method, the main process won't be waiting until the process is terminated. So if you don't use join, what will happen is the main process is going to try to execute, and that's going to cause the issue. That means that your spawn process would not be able to finish. Okay. So because they're treated as individual process, we got to make sure that we handle, right, the execution of the process separately. Okay. So when you join, what that will do is going to block the main process from finishing. And then you're going to, whatever that was spawned after, it's going to finish. Once it terminates, then the main process is going to be terminate. Okay. Okay, so I'm going to run an example and then we'll do the next one. So in this example, as you see in the notes, I have a function called fun. And I want to print calling fun. I'm going to have it pause. So we're going to make it sleep for 2 seconds. Then we have a main function. We are going to print main fun. In main, we are going to create an object called P, our target, which is going to be the function fun. We are going to start the process. We're going to use join. And after it's joined, we have print. So we're going to say process P is alive. And in the main, we're going to call main. So when we run this, so as you can see, right, it's going to say main fun, that this part right here. Then we're going to have the calling fun. So now we're going to spawn this process for this function. As we make it sleep for 2 seconds, so you have a pause there. And then for the process P is alive, so it's going to come back here and it's going to check to see if main is executing, and it says false, right? So it's going to pause that, finish this, and then terminates it, and then come here. So you do have that it started, okay? Calling fun, finish out the process that was spawned. Once that's done, terminates, then it's going to complete the main. Okay, so this is how we can implement multiprocessing in a program, and we can have it wait. So in your notes, right, this is the exact program I copy and paste it. This is the output. So here it tells you that finishing main message is printed after the child process is finished. So I think I left that yeah, I took that off. So let me fix that real quick. So if we add this line in here and rerun it, so it waited 2 seconds, check, right? So as I finish out fun, then it pauses, it verifies that my main is not executed, and then after that, it's going to finish my main. So what that does is it's going to lock it from finishing, and it's going to let the child process, which is this, execute first and terminate. So you can prioritize your processes this way to handle your task. Any question? Okay, you can also test that out. There is an example, another example for when you do multiple join. So in this example, you are going to do a join order. Okay, so let me run this. Oops. So here's my join order. Similar to the last one, this one have more, it would have more spawn and join throughout. Okay. So you have multiprocessing module, you can import in the time. I have a function called fun, pass val. We want to print out starting fun with, and then pass the val, have it sleep, and then print finished fun. In the main, we have P1 as the first object. It's going to execute the function and the arguments. Then we're going to spawn that first process. Now I comment at the join here, right? So I'm going to spawn 1, 2, and 3. And instead of doing them individually after each one, I want them all to start, and then I want them to execute, right, before the main. Okay. So when we finish, then it's going to print finish main. We're going to go ahead and run this. Okay. So you saw here that we start. And again, coming back to what we said about last week, it doesn't necessarily have to be in order like 1, 2, 3. Okay. So we spawn 3 processes and it tells you the time, 2, 3, 1 seconds. Okay. So things might be also out of order. Therefore, we would have concurrent or asynchronous. Then we have it finished. So now it's going to finish 1, 2, and 3. And then after that, it's going to finish main. So because of the join, right, it's going to prevent main from completing. Otherwise, you're going to have main completing first before the sub-processes. So if you want to use one function and use that same function to be able to represent each of the process, this is how you would do it. You would create the object for each of the process, and then you would spawn. And then after that, you would have it join. And then after those terminates, then the main is going to execute. Okay. All right, so let's now look at number 6. So we would refer to multiprocessing documentation given the below program, which implements processing module in Python. Explain how start and join are used. And so this is what the example that I showed you, right? We want to print out the parent and the child process ID. Okay. We have a function, and this function is going to be for the process. We have an object, we're going to spawn, and we're going to have it join. So it's going to wait till the subprocess is finished, terminates, and then call the main. So here is the explanation. Processes are spawned by creating the process object, then calling its start method. So when I create the process object P, after that, I'm going to have it, I use the start method to spawn. Because I use start, it must be called at most once per process object. So if I only have one process, then I can only start one at least once. So in the second example that you just saw before this, you saw that I have 3 processes, so I can start it 3 times. So in this case, we have 1, so we're going to have 1 start. And it would arrange the object's run method to be invoked in a separate process. So when you spawn it, it's going to use the run method or invoke the run method. Okay, that's in the back. Then for join, the join method blocks the execution of the main process until the subprocess, I would say the subprocess, whose join method is called terminates. So it's gonna not execute the main until the call for the subprocess terminates. Otherwise, the main process won't wait for the termination of the subprocess. Okay. So you must use the join to make sure that main doesn't execute before it. Any question? Now, coming back to here, right? You saw that I had commented this out. So this is when we start all of them together and join all of them together like this. What if we remove this comment and then we can comment this out? So we can join them separately. Okay. So we still have the start and the join for individual process. So I have P1 start, P1 join, P2 start, P2 join separately instead of all together like this. So this is the output for the first round when they're all together. Now we're going to see how it's separate. Okay, so you can see that the output is different, right? It's going to start and finish separately. And then it finished the main. So if you start and join them separately, right, as individual objects and execution, so individual process. So I have P1, it's going to spawn, finish, 2 spawn, finish, 3 spawn, finish. It's going to do that separately like this. instead of all together like before. Okay, so that's the difference, is that if you do it this way, right, it would complete P1, then it's going to go P2, then it's going to go P3, and so on. Now we could put the time module in and we can start the clock and then finish and see what's the difference in the execution time. If we do it this way compared to individual, right, you can see slight difference. Okay. But what happened is it's going to block main until at least the third one is finished here. All three is finished, and then it's going to do the main still because we start and join. But we have to start and finish together. It doesn't start all together and finish all together. So it's slightly different. Okay. So I'm going to uncomment this, as I should, for how the program is, and then we can comment this out. So having them spawn and then join together is better. Okay. But then again, coming back to what we talked about before, really depends on what you're trying to do in your program, right? Your program objective. Okay, because otherwise it's just going to be top down like what we see before, 3, 2, and then 1. Okay, so let's do number 7. Any question? Okay, so we are going to use multiprocessing module. We are going to write a small program. We want to be able to say hello or hi, and then plug in our name, kind of like the example in the documentation. We're going to use start and join method from multiprocessing module. And I just need a screen capture of your script and output. So that's fairly easy. All right. So here's line number 7. First line is going to be the import statement. So you can say from multiprocessing import process. That's the class that we're going to be using. And you can define your function with any name. So I chose to use greet. So I define my function, greet, and I want to pass name. Then I wanted to print greeting or hello. You can say hello or hi. And then we want to pass the name. And I just add the exclamation point for look. In the main, so I would say if namespace is main, we're going to instantiate the object. So here we're going to create object P. And the class we're using is process. Our target always is going to be the function that was defined. So my function name is greet. So I need to put that in here. So whatever the function name that you use here, make sure that you use it for your target. And then for my arguments, the name that I want to use, right? Like you saw in the example, Bob, right? You can use your name or whatever name you like. That's going to be the argument that's going to plug in here. So I'm not done with that line. I need to spawn it so I can start it. So here we're going to start the process. Then we are going to have it join. And if you want to do something here, we can say print finish main. Like that. So we know that main's at the end. Okay, so it's going to call start, which activates the run or invoke the run. Then it's going to wait for the execution of this is complete. Once that terminates, then it's going to do this. All right. So I have the greeting, which executes this function, right? And then I have finish main, which is the last part. So it lets, we are able to spawn the process and make sure that it finished. and then we have the main finished. Okay, pretty easy. So in this exercise, we learned to use multiprocessing module. We're able to spawn a process by creating an object, right? And use that object to access the function. Pass the argument for that function. When we call start, we run that function and we wait for it to finish, and then we execute the main. Any question? Now, you might have more than one function, or you might want to reuse the same function for multiprocess, like the example, right? And you can choose how you want to spawn your process in various ways. If you want to multiple spawn, right? Multiple join at once, and then be able to execute. So in this way, we capitalize on our core, right? So if I have 8 processes to do the greetings, I would just repeat and create those objects, spawn those objects, right? And then keep going back to the same function, just have it greet and then just redo that. We can plug in different names as arguments for each different object. So that means that I can capitalize on my 8-core processor, as each core is going to be able to handle the process if I spawn them together and join them together. That means that I need to start, and then join, right? And it's going to wait for the 8th one to terminate, right? Or all of them to terminate, and then it's going to finish out the main. Okay. Any question? Okay, so this is number 7. Now we can go ahead and do number 8. So we want to modify number 7, and we're going to add in the wait time in the function to print out but in this one, we're going to change it up a little bit. We're going to print out the first name. Then we're going to, that's going to be start of the main. We're going to make it pause for 2 seconds, then print the last name at the end of the main process. So at the start, we're going to print first name, pause 2 seconds. At the end of the main process, we are going to print the last name, which is when the child process is finished. Okay, and then we are still going to implement the start and the join method, and we are going to have the output. So it is a different version of this, where we would break it up into 2 pieces for the first and the last name. Okay, so for 8, this is my full name with the wait. Okay. So in this one, I wanted to time it, or I want to implement time because we have the sleep. So you need to have the multiprocessing import statement. So you would say from multiprocessing import process. And then we have the sleep. So we have to import time. We would have a function, and you can name your function whatever you like. I have a show name function. In that function, I wanted to print my first name, make it sleep. So time.sleep in 2 seconds. Then I'm going to print my last name. And for the main, I have a function called main. I'm going to create an object called P, just like before. Process class my target is going to be the function. So target is function name, like show name here. I'm going to go ahead and spawn. So p.start and then p.join. Then I have if namespace is main. I'm going to print starting main, then call the main function. Then you're going to finish out with print finish main. Okay. So in this one, we're going to print the first name at the beginning of main, wait, then we're going to print the last name at the end of main. So where we go. So as you can see, when I did that, it says starting main. So it's going to do this, right? Then it's going to go and print first name, wait 2 seconds, print last name, then come back here and finish out in main. And so this one shows you a little bit more in how, right, the process will start and join and finish with main. Any question? So through number 8, we expanded on the concept of using multiprocessing module, and we implement the wait, which is the sleep, and you can see how the process is spawned when the function is called. After it terminates, then we would finish the main. So it's going to go to the start of the main, right? Execute the child process, wait 2 seconds, execute the second part of the child process, which is the last name, terminates the call, then it's going to come back to the main and finish it out with the main execution. Any question? Okay. So pretty easy in the implementation, so you can see how that works. Okay. All right, so coming back here. So you wanted to use a good example to use also something similar to this, but I'm going to talk about isAlive. So the isAlive method determines if the process is running. We can check to see if a process is running by using isAlive. So instead of printing out like what we've seen before with, whether it is terminated or not, what we can do is we can pass isAlive, right? And it's going to tell us whether it is running or not. Okay, so let's look at that. So just like what we've seen before, we're calling fun, wait 2 seconds, and that's part of the fun definition for the function. Then we have the main function. We're going to print main function. We created the object. Our target is the function fun. We would start it, join it, and then in the print, so here is where we can check isAlive. In the main, we would call the main function this, and then we would print finishing main. You've seen this earlier, so it's gonna do main fun first, then it's gonna come back and do the child process, so that will be calling fun. And then it's gonna check to see if the process is running, so false. And then once, because it's already terminated, right? Here, so it's gonna say no, it's not running. And then it's gonna come back here and finish it out with main. Okay, so that's how you can use is alive to check if your child process is still executing. And the code is provided here. Now, a way that you can also play with it is if you follow the notes, we can comment out the join, then we can see if it is working. So let's try that. Okay, so if I comment this out, let's clear this, and then we're going to run it. Okay, so a little different than what you saw before, right? I have the main fun, so it did this first, of course. Then it's going to check to see if my process is running, and it didn't execute this yet. So at that point, it's already starting my child process, which is this. So it tells me that it is running. And then it didn't wait for that to finish without the join, you see, because when you comment that out, it's just going to go to the main and did this. And then it's going to do the calling fun. So that comes in after the main. So if you don't have the join, the main is going to execute first. So that's why we always should use join. Okay. And there we go. Okay. Any question? Okay, so for A, make sure that we provide our screen capture of our code and the output. Then for 9, it says refer to the notes, write the Python program that implements multiprocessing module and defines the function that can be used for 4 child processes. The program should display the process ID of the parent and the child processes, provide the screen capture for the script and the output. So let me find my going back to our example for this. Okay, so you can use the notes as a reference. So this is the one that I'm looking at. Okay. So this is on page 6. So in this one, the example already gave you like two processes. And what we want to do is we want to make it 4. So you can follow this template from page 6 to page 7. Let me reread the requirement real quick. It should display the process ID of the parent and the 4 child process. Provide the screen capture. We're going to use the pool map. Oh no, that's a different one. Okay. All right, so we can use this. Okay, so we are going to have the multiprocessing import statement. So you can say from multiprocessing import process. We're going to use OS for our PID, which is our process ID. And we can say, we can use fun, that's fine. So we're going to define a function, fun. And then we want to print out this to separate the process so it looks cleaner, but you don't have to have that. So we're going to have print calling fun, print parent process ID. So on this one, you're going to use the operating system to pull your process number or your process ID. That's going to be for the parent. Your PPID is the parent. Okay, that's the difference. And then the PID is the child. So that's the subprocess. Then in the main, you're going to print main function, print process ID, and we're going to use get PID. So it's going to pull the subprocess here. Then we are going to create the object P1 process. The target is going to be the fun, which is previously defined here. We're going to start P1. We're going to join it. Then we are going to have P2. Same thing. And then we're going to have P3. And your P3 is going to have a start. And P3 is going to join. And then the same thing with P4. And P4 is also going to have a start. And P4 is going to have a join. Okay, so make sure we have 4. Then for the last part, we're just going to have if namespace is main, then we're going to call main. And let me save this. Okay, so for me, I have the output. It's going to do the main fun. Okay. So at the beginning, it runs this because that's we call main, right? And then it's going to come up and it's going to print out the process ID. So here it's going to go and it's going to print the parent ID. Wait. Okay, so it's going to do this part first. And then now it's going to start with the first process, right? So it's going to give me this part, which is right here. And then the next, and then the next, and then the next. So these are for the 4 objects. And then if you want to check to see if it did the join properly, or you can say, you can use the is alive if you want, you can throw that in there. But ultimately, that's what we achieve is we're able to start with the main. Then we are going to set up our process, the child. to show the ID and the sub ID for the processes. Okay. I'm just going to do a print finish. Okay, so it will do this last. So you can use the template that's provided on 6 and 7, and then you can just create the 2 additional objects and start and join them. And then for the main, we're going to just call main. Any question? And again, this also uses OS. So if you run it on a new IDE, make sure that it sees the OS. But we did that in the past earlier chapters, so you should know how to do that by now. So in this exercise, we're able to create multiple objects, spawn, right, the processes, be able to set up the join so that way it would call the function for each process. Once it terminates, then we would finish it out with the last part of the main. Here. Any question? Okay, so that was for 9. Refer to 6 or 7, 6 and 7 on page in your notes. Next, we're going to talk about pool map. And you saw that we were able to use our process class. Now we're going to use the pool class. So you saw that we can create multiple objects, right, for our processes. But let's say that we want to make a set of processes. These are called workers. And we can use the library to apply specific function. So that way it would give us the element list. So it's going to return the list of results for the workers. So what we're going to do is we are going to use the map method, okay, for each of the element in the list, and that list contain the workers or your processes. So it's going to access individual worker. That means that it needs to map to it where that process is going to access the data. Okay. So to use the parallel map, you need to initialize what's called the multiprocessing dot pool object. Okay, that's important. And another important point is that it takes the number of workers at its first argument. The number will be equal to the number of cores in the system. So when you set up your pool of process, you can just give it a name. And in this case, we're using pool. And then we would use the pool class for multiprocessing library. You can also have it stated how many processes in that pool. So in the second line, you can see that we can have processes is 4, right? So then you just define your function as you did before. We would have a list of input. Each of the input is going to be for each of the process. Then for your output, we can have it map. Okay. And through the map method, you would, instead of using target like what we did before, here is where you're going to use your function name, right? So the one part of the parameter is going to be your function name, and the other part is for your argument, which is your input. And so we can use this to execute tasks with the worker processes in using the list or a larger container. This method, the pool map method, is a way that we can iterate through the pool or a container of workers. And each of the tasks can be divided to each process. And so this is equivalent to the built-in map method. So it blocks the main from execution until the entire list of workers are completed. So same like what we've seen before, but in this case, now we would just have a group of processes, put it into the container, use each of them as element, and that's going to block the main from execution until everyone is finished, from all the workers are finished. So the parameters we have would be the output, and that's going to be plugged in as argument. So the example below, this one shows you how to do CPU count. We have the time module, the time it with the timer, multiprocessing module. And the function is called square, so we simply take n times n, but with that we also need to make it sleep for 2 seconds. In the main, we start the timer. We want to start with counting the number of core that we have in our computer. So you can do a print starting computation on, and then your parameter would be CPU count for cores. And how that comes in is we have that here from the module. So CPU count, that's underscore count. Then we're going to pass the value for n. So our values, these are just going to be in the tuple 2, 4, 6, 8. Now, this part is where we create your workers, the pool of workers. So we would say with pool class as pool. For our result, res, we're going to use the pool.map. So the map method is used here. And for the parameter, we're going to pass the function, which is square, and then the argument, which is your values from the tuple. We're going to print out the result. We're going to stop the clock. Then we do the subtraction for n to start, so we can get the actual time that it took to run. And then in the main, it's just going to call main. Okay. So I'm just going to take away these for now. So we're just going to use 2, 4, 6, 8. So let's run this. So it tells me that I'm starting on the 8 core. And the output 4, 16, 36, 64. So it squared these, right? So it was able to do this for each of these. Okay. And the elapsed time for me is 2.280619 seconds. So roughly 2.3 seconds or 2.28 seconds. Now, let's say that we add more values. So I'm going to go 2, 4, 6, 8, 10, 12, all the way through 20 to see if there's difference in time because I have 8 cores. So let's see. So when I square these, because I have more input, right? More value for n's. Remember that this is a loop. So I have the result in a list and it is almost twice as long. So 4.25 seconds. So you can see that as I'm using the workers, even though with the cores, the more input I have, of course, it's going to take longer. So I can go further, right? I can keep going, and the higher the number of inputs, of course, I'm going to see my elapsed time also increase. There's the direct relationship there. Now, in this one, compared to the last part that we talked about with the start and the join, those methods are used for individual subprocess or process. When you're doing a pull like this, when you're using a map, you don't have to start and join there, right? Using this, it automatically blocks the main from finishing. So it's going to compute all the way till the end of the tuple here for the values. Okay, we'd square those and then finish it out with the main. But we would see that also the time increase as our input is higher. Any question? And then there's also example for star map. So when you need to pass multiple arguments to the worker function, we can use star map instead of the map method. And it is iterable. So here you would see that it uses star map. So in the case that if I want to use 2, 2, 4, 3, 5, 5, so multiple input like this, I would use star map. So basically it's gonna be able to access where the data located, right? And then plug those values in here. So let's look at the difference. So for these, when I use the star map, right, it's able to square them. And I have 1.27 seconds. And you can expand the number of input. Like I can do 6, 6, this, 6, 6. We can do 8 and 9. So even if I add 2 more, let's add another. Let's say. Let's see if it's different. So I'm going to comment this. Okay, so it produces the output and not a huge difference, right? I started with 1.25 or 1.28 and then 1.27, so roughly the same. Okay. So we're still able to compute the square for those values. X or the mode X times N. Okay, so now actually X to the power of N, we have the next question. So for 10, describe the functionality of pool map in parallel programming. So the pool controls the pool of worker processes to which jobs can be submitted. It can take the number of processes as parameter. We do not need to provide any value. We probably don't need this. The pools map method divides given iterable into several chunks, which it submits a process pool as a separate task. It is parallel equivalent to the built-in map method. It blocks the main from execution until all computation is finished. So what this does is it would be able to have a group of processes as parameter. That's one key point. It's able to divide the iterable into chunks and make sure that they are separate tasks. So your group of processes are able to handle separate tasks. That's what it's saying. So you can run those examples and see how map works and how star maps work, right? You can change up the values or add more input and see how it would be different in time. Then we should talk about the last part and then also finish up with lock. So I gotta talk about Func Tools. Okay, so we talked about how we can use star map with multiple parameters for input. Then there is a thing called Func Tools that allows you to use multiple functions. So here you can see that we have increment, decrement, add. These are separate functions. And then, so what we want to do is we also have smap, and we're going to return f. So in the main, we can use increment first, and we would have func tools dot partial. So it is one function from the list, and we are going to call on inc for increment and then pass the value. So it's going to take this value, plug it into this function, compute it for this process, which is finc. That's the object we built. Then the second object, fdec for decrement. Again, we're using func tools, and we're going to pass the function dec here, and then also put in or pass the parameter as the argument here for 2. So you are going to use func tool partials again. And then lastly, we're going to add. So that's a third object, right? Pass the function. And then here we're going to add 3 and 4 as it requires 2 input. We create a pool of worker. So result, we are going to use pull map method, and we are going to call smap here, or one of the parameters is going to be the smap function. The second part of the parameter, the third and the fourth, is going to be the list, right, of object that we previously created. So finc, fdec, and fadd. So this is how you can use separate function, one for each process, and then you create the object to represent that process and utilize individual function, and we're going to print. So, oh, this is such a, sorry. Let me see. Did I put that one in? Maybe not. Hold on 1 second. I want to run this. Okay, so you can see that's able to give us increment, decrement, and add. Okay. So we didn't print too much there where it would be executing what, but fairly fast, and you can put the timer on it if you like. Okay, last part. So that's how Func Tool works. Executor Interface. For asynchronous execution, we can use thread pool executor, or a way that we can separate the processes using process pool executor. So if you need to separate the threads, you use thread pool executor. For the process, you would use process pool executor. And we can implement the interface. So what that will do is it's going to use the pool of threads for the thread pool executor to execute the call asynchronously. And so this is a way that you can create thread pool using the interface or an executor subclass. Okay. So the example that you see here is we can implement executor, and it's going to create, so we need to also create the object executor, and that uses thread pool executor. We can set up the number of workers, so in that pool, similar to what you've seen before. Then we can have it execute, right? A is going to wait on B, and B is going to wait on A. And in this example, we are implementing the wait, so that allows us to also implement what we would see in the thread as futures. And for the computation, we want to have 5 to the second power. So this is a way that you can set up your thread pool, and you can specify the number of your workers in the pool. Now, one of the important area that I want to highlight when you implement future instances, to create that, you need to use what's called executor submit. This is what you see here. Okay. So another way that we can say this is we can make it, basically we're scheduling the task that's going to execute in the future time. Okay. So in order to activate that, you would use the executor submit. And they tell you here that it should not be created directly except for testing. Okay, so now you can also use concurrent future wait or we've seen in the past as completed. Okay, so when we did the coroutines last week, we talked about how we would use future as completed. So this is also another way that you can implement future instances. Okay, so we'll do a little bit more practice with this, but this is the executor interface. So to answer this question, number 11, when using executor interface, what is used to extract the result from future instances? You would use concurrent future.wait and concurrent future as completed functions. After your result is extracted, it's going to store futures.result. Okay, that's where you can find your result. But to extract the result, we would use these. And you can find the information for executor interface for asynchronous execution on page 10 here. So at the end of that paragraph, it says deadlocks can occur when callable associated with the future's wait on the results of another future. So if I have A wait on B and B wait on A, this is going to happen, right? Because as it's calling, the callable associated, it waits on each other. So that means that it's just going to wait a long time. So that brings us to synchronization unlock. We talked about how multiprocesses can be implemented using this module, and we know that we can put it into the same location. You can use your multiprocessing value method to pass different type of data. The example is shown there. Okay. So here, we would use the dot value. So you can have float, right? Integers, etc. And for your server process, you can also use a manager method. This controls server process, and it supports different types. So you can also take a look at the type of it used. Okay, so there are two methods that you can use to stop process: terminate and lock. So when you use process.terminate, it stops the process that is liable to cost for any type of shared resources. So if there's a hang up, right, with the process, you can use terminate to stop the process. So when you have a lock, a semaphores, things like that cause hang up, we want to terminate that. If it becomes broken or unavailable, that could also be the cause. So if you have a lock in one of the process at a time, you can lock a process by using a lock method. This prevents other process from executing. And it protects that section of the code so that way it's not overwriting or overwriting the actual block of code. So the way that you create a lock is you would create an object, and that would use the lock class from multiprocessing module. Okay. So the example here, you would see that we have the object, we have a class, and it's instantiate. This is a superclass for the process. We set up the counter. In the function, we have a loop. I'm going to go to 1000. So to activate the lock, we would say with lock, and then we would use the counter.value for the increment. When that finishes, it's going to release the lock. Okay. So this is considered synchronization primitives because this is the way that we can lock a process into place. So that way we can protect that section of the code from other processes from executing over it. Where terminate is where we would end a process or stop a process. Where lock is a way that we can prevent other processes from executing. So in number 12, we would say that lock method prevents multiple processes from executing the protected section of the code at the same time. And you would see it again in the future when we talk about how we can lock certain things into, we want to make sure that certain things execute at that time and prevent the others from executing. So in the later chapter, it's going to come back up again. So for the lock, you can find that on page 13. Then in the next part, it talks about OpenMP and CPython. So Open Multiprocessing is an API. You can implement this for C, C++, Fortran, and, including different type of OSs, Solaris, Linux, Mac OS, and Windows. So you can use OpenMP to implement multiprocessing. And it is an implementation of multi-thread for parallelizing the thread. So check out the reference guide. I put a little snippet in here. This will require you to use C compiler. Okay. So there are options for you to implement CPython and OpenMP for parallelizing your program. Automatically parallelism, one of the library that you can use is called Deno, and this is a Python library. It also utilizes a compiler. This can be used for computation with for matrix, mathematical computation. It is open source. Okay, so it gives you the background for Deno. Closely work with NumPy. And it talks about dynamic C code generation. And it is faster because it evaluates the expression faster and so on. So there's some example there for you. So last thing that I want to hit today is TensorFlow. For those of you who go into data science, AI, right, learning machine learning, you would most likely, when you look into ML, a lot of the times you hear TensorFlow. And TensorFlow is one of the product, not the only product, but one of the products that you can implement for machine learning. So this is open source platform, and you can visit their website to learn more. They have great tutorials and resource on the website. It makes it really easy to learn. And even Google have a bunch of stuff for TensorFlow. This is used to create machine learning models. They have pre-built model from TensorFlow, but you can also use it to make your own model. That means that we can create and build training model for whatever we like to do. So for example, if I want to create a model that entail tree leaves images to be able to recognize whenever that I scan a picture of a leaf and it's going to tell me the species of the tree, I can do that, right? I can feed it different images and be able to create some kind of, pattern and train it to recognize specific shape, size, length of the leaves, the leaf veins, the color, and so on. So there are different criteria that we can implement in the train model. So overall, when you're using TensorFlow, you can use high-level Keras API. This is going to make the process a little bit more simpler to integrate. And so ultimately, this is a common product that you're going to see for machine learning. TensorFlow doesn't compile function in C, but it uses machine code, similar to what you've seen with TNO. And so it will be something like this for the example. And there are simple models that you can see. So this one is using Keras. Okay. So you can set up and train model like this. Now, when you run this, you got to make sure that you install your TensorFlow. And so I put the link there for you to download and install. So that way you have, right, the API to be able to apply for your model. And you can read the user guide, the beginner guide. It's really easy. Okay. So the last part on this. So TensorFlow is an end-to-end open source platform for machine learning. It offers multiple levels of abstraction, so you can choose the right one for your needs. It basically is used to build and train models, and it by using high-level Keras API. And then you can install TensorFlow with Windows, Linux, and Mac OS system. You should use Visual Studio for Windows, but ultimately, if you're using Terminal in Linux or Mac OS, you can do pip3 install. And then if you do it for the user, you would do -- user upgrade TensorFlow. Okay. And if you just search TensorFlow, you can find a lot of information by just visiting their website. So likely, if you take machine learning class or explore this topic, you will see. So you can go through. And then there's tutorials, there's guide. So for beginner and for expert, they broke it up into different sections. You can also access some of the learning modules with JavaScript and so on. And then if you click install, it talks about the Python package that you need. If you use Ubuntu, if you're using Windows, if you're using Mac OS, and then other areas of GPUs. So where did I get my answer for that one? Pip install upgrade. So you need to have pip if you're doing it through command line, or in our case, it'll be pip3, because if you have multiple version of Python, then you can do pip install TensorFlow. I actually should put this for my answer here. Okay. And then there are other options in the user guide that you can look at. And then if you want to work with ML for your app, right, it walks you through on how to do that. So definitely useful resource. And then there's API sections. Okay, so that will be for the ML. Any question? All right, so a little longer today. I try to go a little slower. So if you have questions or, so I suggest that come back to the notes, looking at different set of codes, be able to work through and then understand parallel processing a little more. And then we are going to be on this topic when we look at Amdahl's formula next week, and be able to look at how the speed up is going to be with our parallel programming. Okay. Right. Okay, I'm going to go ahead and stop recording. Please put your name into the chat for attendance. I'll stick around for a few minutes in case you have questions. Have a good night.